Welcome to the Joint Universities Accelerator School, and welcome to this preparatory course on classical mechanics. My name is Rasmus Ischebeck. I work as an accelerator physicist at the Paul Scherrer Institute in Switzerland, and I will now introduce you to Hamiltonian mechanics. For some of you, this may be already a repetition of what you remember from your physics classes. For some of you, this may be new. In the end, in any case, I will give a number of books if you want to deepen your knowledge on the subject. In any case, I hope that this will prepare you well for the upcoming lectures on beam dynamics in the Joint Universities Accelerator School. The goal of this lecture is to recapitulate some aspects of classical mechanics that are often used in accelerator physics. We will start with Newton's mechanics and special relativity, and then look into an alternative formulation of the equations of motion, the Hamiltonian Formalism. This allows us to do variable transformations that will be very useful in describing not only how a single particle moves in an accelerator, but how the particles within particle bunches behave. And in a final step, we will define average properties such as beam size and emittance. These properties, beam size and emittance, are key aspects of many applications of particle accelerators, and understanding the theoretical foundation of them will help you appreciate how they can be controlled and manipulated within the accelerator. 1665. Isaac Newton was in his early 20s when the Great Plague hit the city of London. His university, Cambridge, sent students home to slow the spread of the pandemic. Isaac spent his time at home in Woolsthorpe Manor, and he made wise use of his time. Legend has it that, sitting under an apple tree, he discovered the laws of gravity and the laws of classical mechanics. The change in momentum, dp over dt, is equal to the force F. P, the momentum of the particle, is the product of its mass and its velocity. And of course, you know very well how velocity and acceleration are defined. Velocity is the temporal derivative of the position, and acceleration is the temporal derivative of the velocity. So the force in the end is equal to the second derivative of the position of a particle in time. The kinetic energy of an object is given by 1/2 mass times v squared. Newton also discovered the laws of gravity. This can be ignored for accelerators. We are interested in electromagnetic forces, however. The electromagnetic force is given by the electric field E and the magnetic field B. And the electric field E, the proportionality is just the charge. And for Q, this is the velocity cross B. So it acts perpendicular to the direction of motion and perpendicular to the magnetic field. Newton's equations of motion use time as an independent variable and set up now a second-order differential equation for the location of the particle. The location of the particle is given in 3 dimensions with the vector x, y, and z. This, of course, you all know, but it's good to keep this in mind for later. Albert Einstein, in the 20th century, discovered that the relationship between velocity, momentum, and energy is different when the speed of the object approaches the speed of light. Indeed, we have the following relation. The energy squared is equal to the mass squared times the 4th power of c, plus p squared, the momentum squared, times c squared. Note that we use the same letter E here for the energy and the electric field. This is somewhat inconvenient, but we will use the vector E for the electric field and just the E for the energy. For a particle at rest, we find that E equals mc squared, probably the most famous formula of the 20th century. This energy of a particle at rest is called the rest energy. The momentum now of the particle is no longer just m times v, but it's m times gamma times v. Gamma is defined here as 1 over the square root of 1 minus beta squared. And beta is the velocity in units of the speed of light. So the momentum p is equal to m gamma beta c. With the electromagnetic force and with the law of motion corrected for relativistic particles, in principle, we have everything that we need to describe particles in an accelerator. Accelerator physicists, however, often use a different formalism, which I will describe in this lecture. It is important here to note that the formalism is the only thing that changes. The motion of the particles is exactly the same as if we computed them directly from Newton's law of motion. And this formulation of classical mechanics is called Hamiltonian mechanics. William Rowan Hamilton lived from 1805 to 1865. He introduced a formalism that allows us to derive the dynamics of a system. And you can already see that while he lived before Einstein discovered the special theory of relativity, we can still use this formalism today. And that shows the real power of what we can do with this. We will start with a function h, which we will call Hamiltonian. This h is simply the total energy of the system, so kinetic energy plus potential energy. Each degree of freedom, that is, each dimension in space for a single particle, is described by a variable pair now, x px, y py, and z pz. And these are now the position and the momentum of the particle. The independent variable, if we first start out, is the time, the same as in Newton's law of motion. The equations of motion, so the temporal derivative of x and px with respect to time, are given by the partial derivative of h with respect to px, and the partial minus the partial derivative of h with respect to x. We can now plot the state of a one-dimensional system in a two-dimensional phase space plot. The phase space plot is shown here, x and px, and the position, the state of the particle is given by these two variables. And we now have two first-order differential equations for each dimension in comparison to one second-order differential equations in Newton's laws of motion. All in all, for the 3 dimensions of space, we have a 6-dimensional phase space. So this is an overview of the Hamiltonian formalism. First question is, of course, that you may ask yourself is, why do we use the Hamiltonian formalism? Why do we do things this way? How do we use it? How do we determine the Hamiltonian for a problem? What are the canonical variables? And then from this, how do we determine the motion of these particles? We will look into this in the following minutes. We will see some examples of Hamiltonians. And in the end, we will very briefly touch the principle of least action and the connection to quantum mechanics. First question, why do we do this? I still remember, I think it was in my second years of studies that in the classical mechanics lecture, the professor introduced the Hamiltonian formalism. And I thought, oh, this is all good and well, but I'll probably never use this again in my life. He was wrong, because I became an accelerator physicist, and in accelerator physics, we actually make use of the Hamiltonian formalism quite a lot. And I hope by the end, you'll understand why we do this. The real power of Hamiltonian mechanics comes from coordinate transformation. And this allows us now to choose different independent variables and different canonical variables with the real physical meaning for our system under study. We can apply perturbation theory if we want to see a small motion on top of a bigger one. Now, how do we actually do this? The Hamiltonian formalism is really already described on this slide here, which you saw before. The Hamiltonian is the total energy of the system. Independent variable is time. We start off with the canonical variable pairs, x, px, y, py, and z, pz. And the equations of motion are the partial derivative of the Hamiltonian with respect to px, and dpx over dt is minus the partial derivative of the Hamiltonian with respect to x. And after that, after we've set this up, we can do variable transformations and further look into details of the system. Let's jump right into an example. We have here a harmonic oscillator, so a mass attached to a spring, and you hopefully remember that if you set this in motion, that this mass oscillates left and right in a sinusoidal way. And if we want to treat this in the Hamiltonian formalism, we start off by writing the Hamiltonian as the function of the kinetic energy plus the potential energy. Kinetic energy is given by p squared over 2m, and the potential energy is k½ times x squared. This is a one-dimensional problem. We have two canonical variables, x and p, and two constants here, k and m, and we call them these the spring constant and the mass. So we now go forward and define the equations of motion. The x over dt is partial derivative of h over p, and dp over dt is minus the partial derivative of h over x. And from this, we very quickly find that the x over dt is p over m, dp over dt is minus k times x, and combining this, we now find that d square x over dt squared, so the second derivative with respect to time, is minus k over m times x. Now, this is the same solution that we find from Newton's mechanics, and that is good because we describe the same system. This differential equation, second order differential equation, has a solution. X of t is given by a times sine of omega t plus phi for arbitrary amplitude a and phase phi. So, why is this the correct Hamiltonian? Where does it come from? Well, first of all, it is just the total energy of the system. The Hamiltonian describes the motion of the mass connected to a spring, and we get the same result as with Newton's mechanics. Of course, you may well say, then let's just use Newton's mechanics right away. And of course, we could do this, but I'll show you in the application of Hamiltonian to accelerator physics about some other tricks that we can do with the Hamiltonian. In the end, of course, the justification that this is the correct Hamiltonian for the system has to be given by experiment, right? In principle, we could build an apparatus like this, and we could verify that this description of the system actually fulfills reality. Note also that in this particular case here, the total energy of the system is constant. So this is, of course, not generally true, as we may transfer energy from external fields. Let's next look at electromagnetic fields. Here we have the Hamiltonian given by P minus QA squared over 2m plus Q times phi, where Q is the charge of the particle, m is the mass, phi and A are the scalar and vector potentials respectively. The canonical variables now are x is the location of the particle, and P is m times v plus Q times A. Now this is the canonical momentum. Note that the canonical momentum is different from the mechanical momentum. Mechanical momentum is just P equals m times v. And the canonical momentum has this additional term with the vector potential A. Also remember that the electric and magnetic fields, while they are of course not given in this Hamiltonian directly, they can be derived from the fields, right? So E is minus the gradient of V minus the temporal derivative of A, and B is the cross product of the derivative with the vector potential A. Keep in mind again that we use E here with a vector for the electric field, whereas we use E without the vector for the energy. In particle accelerators, we usually work with relativistic particles that travel at velocities close to the speed of light. The energy of the particle, as we saw before, is now given by p squared c squared plus m squared c to the fourth power. I'm sorry, I forgot the e squared, of course, here. And E is the gamma times m times c squared. P is beta gamma mc, and beta and gamma are defined by these well-known formulas. In an electromagnetic field now, the energy is given by the potential energy is given by this here, by the Q times phi. And this is now, the first part is the kinetic energy, and the second is the potential energy. And the momentum here is given by beta gamma mc plus q times the vector potential A. This is again the canonical momentum P here. And now the relationship between energy and momentum becomes, so this is the total energy E minus q phi squared. This is times P minus qa squared. This is the canonical momentum P. C squared plus m squared c to the fourth power. And if we solve this for the energy E here, we have E equals c times square root of P minus qa squared plus m squared c squared plus q times phi. This total energy is what we will use as Hamiltonian in accelerator physics. H equals c times square root of P minus qa squared plus m squared c squared plus q phi. More of this in part 2 of the preparatory lecture on applications of the Hamiltonian mechanics to particle accelerator. Before we finish this first part, 2 more side remarks here. The first is the principle of least action. For a particle obeying Hamilton's equations, the trajectory of a particle here in phase space is such that the action, the integrated action, is at a minimum with respect to small changes in the trajectory. The action is defined as this here, p times dx over dt minus h. And if we integrate this action s from point at time t0 to the point time t1, then we find that this integral is at a minimum with respect to small changes. We can also reverse the argument and say that Hamiltonian's equations follow from the fact that the trajectory of a particle in phase space minimizes the action. Another side remark is in quantum mechanics, the Hamilton function becomes the Hamilton operator here, and you see this well in the Schrödinger equation, I times h bar ddt of the wave function is equal to the Hamilton operator times this wave function. In accelerator physics, quantum effects are rare, so we will not go deeper into this subject here, but we will rediscover the quantum effects when we look at synchrotron forces. Now, this was a lot of material. If you want to further look into more details of Hamiltonian mechanics here, I can recommend a few books. A classical book on classical mechanics is by Landau and Lifshitz, Mechanics, and this has also a chapter on Hamiltonian formalism. And if you want to know how we apply the Hamiltonian mechanics to accelerator physics, there's this beautiful book here by Andy Wolski, Beam Dynamics in High Particle Accelerators, and I seriously recommend that you get a copy of this and study it to go deeper into the subject. In the following lecture, we will look at the application of the Hamiltonian formalism to accelerator physics. We will look at variable transformations, look at perturbation theory, and finally, from the action and angle variables, define formulas for beam size, divergence, and emittance. With this, I wish you all the best for JUAS.